Okay, the dot product of u dot v, right, given two vectors, u dot v, and again, that dot might make you think of multiplication, right? But it actually means something a little bit different. If the vectors have their component form, u1, u2, and v1, v2, then the dot product is u1 times v1 plus u2 times v2. Right? It's the first component. You multiply the first components plus you multiply the second components. That's it. That is called a dot product. Yeah.
So like you multiply those and then add them together?
Uh-huh.
Okay. So it's basically like what we did last time. Just multiplication.
Well, this is a combination, right? This is multiplying these together, which is not scalar multiplication of a vector, and then adding together two scalars, right? In the end, there's no vectors on the right-hand side. So I don't really think it's similar to either one of those. We'll see on the next slide when we do the examples, right, to actually practice doing it a little bit. But the properties which are presented in the book, like right one after the other, that's why I'm presenting them that way, are u dot v equals v dot u. Which property does that seem like? A commutative, right? So the zero vector, remember, what is a zero vector? What are the components of a zero vector? 0, 0, right? So the zero vector dotted with a vector is the zero vector, or is actually 0, the scalar 0. U dot v plus w, what property does that look like? Distributive, right? If you dot a vector with itself, you actually get the square of the magnitude. And the last one, if you multiply the dot product of two vectors by a constant, that's the same thing as having multiplied just one of those vectors by the constant and then taking the dot product. So it wouldn't matter if you do c times u dot v or u times dotted with cv. It's going to be the same thing.